because it's our first seminar, a warm welcome to all. Greetings, everyone. And I hope we do have a successful seminar series. I'd like to thank Diane for putting all these talks together. I think we got a good list of talks. And it's always nice to start with group theory, a fascinating area of research. And today we're very fortunate. We have Professor Thekiso Seretlo of Northwest University, Department of Mathematical and Statistical Sciences. Very exciting topic as well. And there are a lot of things that grow out of this topic and related topics. The title of his talk is on two-generation methods of the simple linear group PSL 3,7. And very warm welcome to you, Thekiso, and I hope that everybody will enjoy the talk. Please proceed. Thank you.
Well, thanks very much. As Professor Mohammed has pointed out, my talk is on two-generation methods of the simple linear group PSL 3,7. Really, more than 15 years back, Professor Muri supervised somebody from UWC on these things, and it has been, and most of us, we did Clifford Fisher theory, but as we progressed, we thought, hey, this topic is not being looked after, so me and Ayub Bashir decided to supervise Dr. Mutalane on this on PQR generations. Professor Muri and Faisal, not Faisal, why do I forget the name? They did two-generation methods on PQR generations and P complementary generators. We decided to do, because PQR generators, this is most fundamental. We did two-generation method on PQR generators and also the rank of conjugacy classes. This is the outline of my talk. I'll do the introduction. I'll do the definition. I'm sure these are very basic definitions, basic information. I lacked a better word there. Benside theorem. The Benside theorem is important because the method that we follow in this talk is what you call the structure constant method. And the Benside theorem really defines what the structure constant is. Then we look at some results on generation and non-generation. Then we look at the PQR generations of PSL 3,7. When we look at that, we'll give the main theorem, and then maybe about 2 or so examples. Then we look at ranks of classes of PSL 3,7. We'll give the main theorem, and maybe about three proposals. Sorry, the student that Professor Muri supervised in Western was Dr. Hanif. And the last thing was the bibliography. On the introduction, a final group G is said to be LMN generated, where LMN are positive integers. If G is generated by 2 elements, X and Y, although we say it's element generated, it is generated by 2 elements, X and Y. Some people call this PQR generation a two-generation method. Here, the order of X is L, the order of Y is M, and the order of Z is N, where Z is XY inverse. Some people write it that XYZ is equals to 1. And please note, the order of XY is just equals to the order of Z, which is N. By definition of a triangular group, If you would like to know more about the triangular group, the thesis of Dr. Khanif, I think it was well written. He's written a lot about these triangular groups and whatever. But my main point is that if this group is element generated, then it's sigma L, sigma M, and sigma N generated, where sigma is an element of S3. What you mean is that we can permute this thing. I'm saying if it's element generated, then it is MLN generated, it is NLM, and whatever, whatever. But to avoid repetition, we let L to be less or equals to M to be less or equals to N, just to avoid repetition. And lastly, a final group G and a non-trivial class Nx of G. The rank of Nx in G, the rank of this conjugacy class Nx in G, denoted by that, is defined to be the minimal number of elements of Nx generating G. Let's give them, these are very basic definitions really. The general linear group G, which is GLNQ, is the group of n by n invertible matrices over Galois field Q. The special linear group SLNQ is the subgroup of GLNQ where the determinant of each matrix is 1. And the projective special linear group PSLNQ is the special linear group factored by its center. This has got the effect that it makes the group to be simple. And the last one, I'm not sure that it is necessary. Nx, which is the x in square brackets there, is the conjugacy class of x, where the order of x is n. What you mean by the order of x is n is that x to the power n is just equals to the identity element. Similarly for the conjugacy class my, and similarly for the conjugacy class nz. This, I call it basic information. Really, maybe my English was lacking, but I lacked a better word. If G is 2,2n generated, then G is dihedral. And to all group theorists or people in algebra, a dihedral group is not simple. And please note, if n is a positive number, if you take the inverses, 1 over 2 plus 1 over 2 plus 1 over n is greater than 1. It's greater than, let's just know that. And if it happens that our G is simple, it's a simple non-abelian group. If 1 over L plus 1 over M plus 1 over N is greater or equals to 1, if it is simple, if it happens, then it can be nothing else except the alternative group A5. Otherwise, we're looking for 1 over L plus 1 over M plus 1 over M to be less than 1. Actually, Dr. Khanif did discuss these things. If 1 over L plus 1 over M plus 1 over N is greater than 1, we get what you call a spherical space. If 1 over L plus 1 over M plus 1 over N is equals to 1, this is the Euclidean space. If you can just multiply everything by pi, you'll see this is a perfect triangle. But we're more interested in 1 over L plus 1 over M plus 1 over N to be less than 1. And this is what is called the hyperbolic space. G is said to be a Howitz group if and only if G is non-trivial. We mean, when we say trivial, we mean that G has just got one element, namely the identity element. If G is non-trivial and is 237 generated. Let's look at the conjugacy classes of PSL 37. Just by the way, PSL 37, these are it's a group made by 3 by 3 matrices whose determinant is 1 over a Galois field 7. And the order of PSL 37, when I say the order, the number of elements in PSL 37 is 1,876,896. And those are the prime factors: 2 to the 5, 3 squared, 7 cubed, and 19. And if you look at the conjugacy classes, the group PSL 37 has exactly 22 conjugacy classes of its element. And 12 of these classes, I can say these are prime conjugacy classes because the elements there have got prime order. And these classes are, it's only got one class of 2A, only one class of 3A, 4 classes of order 7, and about 6 classes of order 19. And we look at the conjugacy classes of maximal subgroups. This group has got 8 conjugacy classes of maximal subgroups. The first one is H1, which is isomorphic to H2, but they are not in the same conjugacy class. They're isomorphic, but they don't lie in the same conjugacy class. This happens to H3, H4, H5. These 3 groups are isomorphic, but they're not in the same conjugacy class. H6, H7. Please note H8 is 19 split 3. 19 split 3 is what we call the semi-direct product of the cyclic group 19 and the cyclic group. Structure constant and Benson theorem. Let delta Lx, My, and Z be the cardinality of the set Kelly A, which is an ordered pair from the conjugacy class Lx by My, where Xy is Z. Now, this delta Lx, My, and Z, this is called a structure constant. And we give the Benson theorem as such: if the irreducible characters of G are high 1 to high R, then the structure constant can be calculated in that fashion. These are usually very big numbers, and we use a program that is called GAP. So that's why I've noted that the structure constant for any finite group can be calculated using GAP. GAP is generally an abbreviation for groups, algorithms, and programming. Now, delta star Lx, My, and Z denote the pairs X, Y, in A that generate the entire group G. Now, delta, it generates the group and its subgroups. Delta star, it just generates the group. So the essence of this talk is that what we want to get is to get those elements that generate the group and not the subgroups. That is, we want to calculate delta star. So how do we calculate that? Delta star, from the structure constant of the group, we subtract the structure constant of the maximal subgroups. The summation there is just the structure constant of the subgroups. More accurately, let H1, H2 to HK be a full set of non-conjugate Lx, My, and Z generated proper subgroups of G. Then delta star will be delta G minus the summation of that Hi and the structure constant of Hi, where the small hi is the number of distinct conjugates of Hi containing Z. That is essentially what we try to do. And this is the most difficult part, when calculating this, because what we are looking here for is that how many ordered pairs generate the whole group. So the smallest number that we're looking for is 0. We cannot get negative because we can't have a negative number of ordered pairs generating a group. So we should have the smallest number should be 0. That is, there are no ordered pairs generating the group. Or that should be greater than 0. That is, if delta star is greater than 0, then there are some ordered pairs that generate the group, that generate the whole group. Some results on generation and non-generation. Let G be a finite sim groups such that G is LMX, LX, MY, NZ generated. Then G is LX, LX, M times generated and NZM generated. We can also take it. If G is 2X, MY, NZ generated, then it is also MY, 2X, NZ generated. And we're assuming that here is a simple group. So if it is MY, 2X, NZ generated, then it is MY, NY, NZ squared generated. And going to Volta, we want our delta star to be greater than 0. But we want to be here a little bit careful that our delta star should not be less than the order of the centralizer of the conjugacy class. If it is less than the order of the centralizer of the conjugacy class, then we assume that our delta star is equal to 0, and thus this group G is not LX, MY, and Z generated. I'll just mention Lee and Scott will not be using these two theorems. I'm sure both of them, they seem to be complementary to each other. They really talk about, you can always determine non-generation about them. Scott, for instance, if something is less than, if a group is element generated, then something is less than that. If it is generated, that is less than that. But it does say if it is less than that, then it is generated. So whatever you look for is that whatever you are calculating, if it is greater than, then you know that it is not generated. Re is sort of complementary to Scott. So the method that we'll be using will be known as the structure constant theorem. How do we get these results? The PQR generation of the conjugacy class of PSL 37, these are obtained through a series of propositions. And the next thing that we give will give the main results of the PQR generation and the ranks of the classes of PSL 37. And we give some examples of that. G be the projective special linear group. If it's projective, it is simple, PSL 37. S be BCD and T be ABCDEF. Then G is generated by all triples, by all the triples PX, QY, RZ, where PQR are primes dividing the order of PSL 37 if and only if PX, QY, and RZ is one of the following examples. The group is 2A, 3A, 19Y generated, 2A, 7X, 7X, 2A, 7X, 19Y, 2A, 19Y, and 19Z. Please note, this group is not 2A, 3A, whatever generated. So it can never be Howard's group. This group again is not 2A, 7A generated. We cannot prove that. And if we go to 3A, 7A, 19A, specifically for 3A, we'll see that somewhere this group is 3A, 7A, and 19Y generated, but it can never be 2A, 7A generated. Similarly for 7A, 19X, and 19Y, maybe we'll be more interested in the 2 generated 2A3A, and 3A3 something 3A, 7A. If you want to look at 2QR generations of G, the 2QR generations comprises 3 cases, namely 23R, 27R, and 219R. The condition that this should be in a hyperbolic space, that is 1 over P plus 1 over Q plus 1 over R to be less than 1. That should imply that 1 over 2 plus 1 over 3 plus 1 over R should be less than 1. And if that is so, then surely R should be greater than 6. And the primes that are greater than 6 is only 7 and 19. And also, I'm just repeating that PL37 is not a house group because it is not 2A, 3A, 7X generated for all X element of ABCD. This is just a proposition. G is 2A, 3A, 19Y generated. G is 2A, 3A, 19Y generated for Y in T. When you say Y in T is from A to E. Using gap, we can see that delta G is 57 for all Y in T. And from the conjugate subgroups, we can see that H8 is the only subgroup that contains a conjugacy class of order 19. However, you can see that the order of H8 is 57 actually, which is odd. So it means there can't be any 2A, any subgroup of 2A that goes into that, into the main group. So what does this mean? It means that there's no subgroup, there's no contribution from any maximum subgroup of G to that 2A, to delta star 2A3A 19X for X and T. So what it means is that delta star is just equal to delta G is 57. Hence G is generated by all triples. G is neither 2A, 7A, 7X, where X is BCD, nor 2A, 7I, 19Y. And now we can always prove this. If you calculate delta G for both, it is 0. Delta star is less or equals to delta G. So it means that the delta star is also 0. What does this mean? It means that there are no ordered pairs XY that generate G. So G cannot be generated by those triples. This is the main theorem. Let G be a projective special linear group, PSL 37. Then the rank of G2A is the rank of G3 of G7 is 3. What we mean is that there are at least 3 elements of 2A or 3 elements of 7A that generate G. And for the rest, there are only 2 elements of any other conjugacy class that generate G. And the only one that you can leave besides 2A and 7A is the identity element, the identity conjugacy class 1A. Let's show that rank of G2A is 3. The rank of GA2A is 3. We have proved even on this talk that G is 2A, 3A, 19Y generated. So if it's 2A, 3A generated, it means it's 2A, 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 19Y raised to the power 3 generated, or to the power 3 generated group. That is G is 2A, 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 19Z generated for some Z. Therefore, the rank of G into A is less than or equals to 3. But we know that G cannot be generated by 2 elements of 2A, otherwise it would be a dihedral group. So it should follow that rank G2A should be greater than 2. If it's less or equals to 3, then it means that the rank of Ga2A is 3. The next one. Similarly, the rank of G7A is 3. I said, please note that the rank of G7A is not equal to 2. So we've also got that G is 3A, 7A, 19Y generated. So if it is 3A, 7A, 19Y generated, it must also be 7A, 3A, 19Y generated. And if it is 7A, 3A, 19Y generated, then it might be 7A, 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 19Y to the power map 3 generated group. That is G is 7A, 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 19Z generated group, where Z is any element of T. Hence, the rank of G7A is less or equals to 3. But the rank of G7A should be bigger than 2, so it should just be 3 and nothing else. Other conjugacy class, for the rest of the conjugacy class, except 1, 2, and 7, the rank of G from those conjugacy classes is 2. That is, the group can be generated by just 2 conjugacy classes from these. If we test, I didn't take all, I just took a few. If delta G is just delta G nx nx, that is 2 generated. And summation, that is the delta in subgroups. Delta star of G is that. Using gap, we can always calculate that. For 3A, delta G is 2,850. The number of conjugates of 19A in H8 is 1. The structure constant of H8 is 0. So if you multiply that by the number of conjugacy classes, it's 0. So delta star is delta G. So it is 3A, 3A, 19A generated. You can go to the last one, 19G, 19T. Delta G is 5,645. The number of conjugates of 9A is 1. The structure constant in H8 is 2. If you multiply it, 1 times 2 is 2. So just removing the delta, the summation, the structure constant of the maximum subgroups from what you've got in the left, you're left with 5,643. That's quite a big number, which is far bigger than the centralized of that. So this group is indeed 19T, 19T, 19A generated. So it follows that the rank of G and X is 2 for all NX in R. This is part of the bibliography, could have been more, but for the sake of space, I just did that. Actually, me and Bashir did one for PSL 35. I just decided